Good afternoon. My name is Adam Gramlich, and today we are going to be talking about 7.2, which is probability theory. So if you're ready, let's hop on into it. Now we're going to be talking about three different separate topics here. The first two, assigning probabilities and independence, are going to be our intermediary topics. Just getting us used to probability. We're going to be going through a couple definitions, a couple connections, and then a few examples per problem. And then we get to the infamous birthday problem, where we're going to be looking at a problem where it's our job to find the minimum number of people in a room. So the probability that the two people share the same birthday is greater than 50%. So if you're ready, let's move on. We're going to go to definitions. We're going to start with assigning probabilities. So we define the assigned probability to each event in a space S as little p sub s. P is the probability, S is the event in the space. Big P is usually denoted as a whole probability, as all of the outcomes. So for this, two conditions must be met. 0 must be less than or equal to P sub xi, where x of I is an individual event, is equal to 1. This makes sense because no event can have a probability that's greater than 1, and no probability can have a negative probability, which is less than 0. For 2, all individual well, individual probabilities add to 1, meaning that starting from I equals 1 to n, the summation of all pxi's is equal to 1. All the events in the space need to total the entire space. There can't be a gap off to the side. So if we generalize that and write it out, we could do p of x1 plus p of x2 plus everything all the way up to p of xn would be equal to 1. We call these probability distributions, the most famous of which we're going to call the normal distribution. Notice that if you integrate the normal distribution, the area under the curve is 1, which makes it a great probability distribution. Now, another distribution is known as the uniform distribution, and this is if all events in S have equal probability. An example of this is a coin flip, where heads and tails have equal probabilities. On a graph, kind of looks like this bar notation. For events E, the probability of event E, if event E includes, say, n outcomes, it's going to be the little probability of event x1 plus the little probability of x2, all the way up to the little probability of xn, all events in E. Let's move on to some examples here. Assume a spinner with numerical options 1 through 4. The spinner has 4 quadrants. So if we were to assign probabilities for landing on each of these, assuming this is fair, each one has an equal likelihood of 1/4 to be landed on. Now, in order to adjust for fairness, let's write this out. We have probability of 1 plus probability of 2 plus 3 times the probability of 3 plus the probability of 4. Overall, we have 6 total probabilities. So we're going to split this into sixths, where 1, 2, and 4 have a likelihood of 1/6, and 3 has a likelihood of 3/6, which is 1/2. Now, if I were to find the probability of landing on an odd number in the fair spinner, I'm going to add up all the odd events. In this case, 1 and 3 both have a probability of 1/4, so 1/4 plus 1/4 is going to be 1/2. On the unfair spinner, we're going to do the same thing, except we are going to have different probabilities. This time 1/6 for 1 and 1/2 for 3, which add up to a total of 2/3.
Hey everyone, my name is Ryan, and today we'll be looking at probability theory. We'll take a look at complements and unions of events, Bernoulli trials and binomial distributions, and then we'll take a look at Monte Carlo algorithms. Let's start with complements. In any probability setup, the total probability of all possible outcomes is always 1. That just means something has to happen. Either the event occurs or it doesn't. Now let's say we're taking a look at event E. Let's say the probability of E, or P of E, is the probability that it rains tomorrow. And let's say that's 30%, or 0.3. Now, if we want to know the chance it doesn't rain, or E complement, we're looking for the probability of the complement of E, written as P of E complement. To find that, we just subtract the probability of E from 1. So we have 1 minus 0.3 to give us 0.7. So there's a 70% chance that it won't rain tomorrow. Now, let's say we want to know the probability of one thing or another thing happening. Like, for example, what's the chance I draw a heart or a queen from a deck of cards? Let's make event 1 drawing a heart, and event 2 drawing a queen. Out of 52 cards, 13 are hearts and 4 are queens, but one card is both, the queen of hearts. If we just add 13 and 4, we'll get 17, but that counts the queen of hearts twice. So we have to subtract the one overlapping card to get 16 out of 52. This is the whole idea of the inclusion-exclusion principle that we've dealt with throughout the semester. Now, if two events don't have an overlap or are disjoint, then we won't have to subtract anything. This formula generalizes it a little bit. If you have a bunch of events that can't all happen at the same time, or in other words, are pairwise disjoint, the total probability is just the sum of their individual probabilities. Now let's say 3 people are running for student body president. If one of them has a 40% chance of winning, one of them has a 30% chance of winning, and another person has 30% chance of winning, the probability one of them wins is just 0.4 plus 0.3 plus 0.3, which is equal to 1. Notice again there is no overlap because 2 people cannot both win. Thus, we do not have to subtract anything.
Two events can be considered independent if their joint probability equals the product of individual probabilities. So for this theorem, two events E and F are independent if and only if the probability of E and F is equal to the probability of E times the probability of F. Let's test that on 2 examples. At a restaurant that serves either chicken sandwiches or hot dogs, let event A be where a family with 4 people orders 4 chicken sandwiches, and event B be where a family with 4 people orders at least 2 chicken sandwiches. Are events A and B independent? At first glance, you might be instantly able to say, no, these are not independent because they depend on each other. But we're going to prove that mathematically. For the first one, the probability of each individual person ordering a chicken sandwich is 1/2. So if I do that to the 4th power for 4 people, the probability is 1/16. For event B, it's probably easier to look at the probability where it doesn't happen. So we're going to complement it and look at all events where it doesn't happen. Well, there's 5. You have hot dog, hot dog, hot dog, hot dog, and then all combinations of one chicken sandwich. This is 1 minus 5/16 or 11/16. So probability of A times probability of B is equal to 1 times 11 over 16 squared, or 11 over 256. For A and B, we need to look at probabilities where they have both of these. Well, that's going to be 1/16, because there's only one event where it has all 4 and at least 2. Now, are these 2 the same? No. Therefore, these are not independent. For our second example, let's say you flip a coin 3 times. Note that 2 to the third is 8, so the total amount of outcomes we have is 8. Let event A be where you receive alternating outcomes, and event B where you get at least 2 tails. Now for event A, there's two possible outcomes for this: heads, tails, heads, and tails, heads, tails. The probability of this is 1/4, which is also the same thing as 2/8. For event B, getting at least two tails, let's get rid of all the events that don't have at least two tails. So heads, 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 and all combinations of tails, heads, heads. So there's three. Probability of this is 1/2 or 4/8. So if we multiply these together, 1/4 times 1/2 is 1/8. For A and B, there's only one outcome where it has at least two tails and alternating, and we've outlined it right here. So the probability of that is also 1/8. And because these are the same, these two events are independent.
Now moving on to Bernoulli trials. These are just experiments that have two outcomes, success and failure. Think coin flips, yes or no survey questions, hitting or missing a shot. The probability of a success is denoted with a P, while the probability of a failure is denoted with a Q. Since we can't have both a failure and success happening at the same time, or in other words, these two events are disjoint, we have P plus Q equals 1. Now let's say I flip a biased coin where the chance of heads is only 33%. If I flip it 9 times and I want exactly 6 heads, what's the chance of that happening? First, we'd calculate how many ways to get 6 heads out of 9 flips. That's the combination part right here. Then we multiply by the probability of heads happening 6 times and the probability of tails happening 3 times. We get 224 over 6,561, or roughly 3.4%. So even though getting heads is rare, this gives me the exact probability of that specific outcome. We can also see here that the trials are independent and each outcome is unaffected by other outcomes. This formula here generalizes that idea. If you're repeating a trial n times and want k successes, this is how you calculate it. We take the combination of n choose k multiplied by the probability of success raised to the number of successes multiplied by the probability of failure raised to the number of failures. And the number of failures is just the number of trials minus the number of successes. Now, say you're running a machine that has a 90% success rate, and you run it 10 times. What's the probability it works exactly 8 times? Well, we can plug that right back into the formula up here. So we have the combination of 10 choose 8 multiplied by the probability of success raised to the number of successes multiplied by the probability of failure raised to the number of failures. And we get approximately 0.1937, or a 19% chance the machine works 8 out of 10 times. What we're looking at here is the sum of all the probabilities for getting 0 through n successes. Each term in this sum represents the probability of getting exactly 0, 1, 2, up to n successes. But this whole expression on the left is actually the binomial theorem. So we're just using that theorem in reverse. And since p plus q always equals 1, we get p plus q raised to the n equals 1 to the n, which will always equal 1. So the total probability of all possible outcomes from 0 to n successes is 1, like we'd expect.
Birthday problem asks for the minimum number of people needed in a room for the probability that two people sharing a same birthday to be larger than 1/2. We're going to assume that each birthday is independent, each birthday is equally likely, and we're also going to assume that we have 365 days in a year. I'm not going to work this out, but by the definition of a complement, we're going to look at all the probabilities that they have different birthdays. So for the first person, 365 over 365. The next person's probability would be 364 because they have one less day to choose from. Then 363, all the way down. And we're going to keep doing that and take the complement of it. Since this is all different days, we want the same day. And we keep doing this until this number exceeds 0.5, meaning we've exceeded that 1/2. Let's practice with a different example. Let there be 200 unique restaurants. Each person who enters the room selects one restaurant as their favorite. How many people must enter the room so that the probability of two people choosing the same restaurant is greater than 60%? So the first person will always choose a different restaurant. The next person is one less. The next person is one less than that. If we take this, continue it, and complement it, so you do the math off screen, it takes around 20 people to do this, with a probability being around 0.626. That's going to do it for my section, guys. I hope you enjoyed. And as always, let's learn discrete. Peace.
My name is Rouse, and here's my final project for Math 381 Honors. It is on Chapter 17 of the textbook, Probability Theory, and my portion will be on Monte Carlo solutions. So, to give you a basic overview, I'll give you an introduction as to what a Monte Carlo problem is, as well as a simulation of pi and the usage of Monte Carlo problems in finance to give a broader scope as to what these formulas and methods are useful for. So, what is a Monte Carlo problem? Monte Carlo problem is any problem involving estimating a numerical result, such as a value, probability, or solution to an equation, or performing many random experiments and then analyzing the results. These algorithms are probabilistic, meaning the rest of the algorithms we've seen in this course so far are deterministic, meaning they result always in a certain value or values. But probabilistic methods use random decision trees to lead to a conclusion. This means that there's a chance that an incorrect result is created. This can be minimized by the use of higher number of random decisions. More accurately, Monte Carlo problems are examples of heuristics that find a good enough solution that's not always perfect to the most complicated problems. To understand Monte Carlo simulations, a basic understanding of three statistical concepts being Bernoulli trials, the law of large numbers, and expected values is required. Bernoulli trials came up earlier in the course and are random events that produce two possible outcomes, either true or false. They can flip a coin and assigning heads is true or tails is false. And then the law of large numbers, which is a principle in statistics indicating that an increasing number of random samples predicts that results will converge around expected value. This makes sense. The more coins you flip, the more likelihood that you'll get 50% heads or 50% tails. Though this is not certain. And expected values are the sum of the weighted means of a probability distribution. The center of a probability distribution is another way to call it, or also what a random series of trials will converge onto if you're allowed to continue into infinity. On the left, we have the formula for discrete probabilities, and on the right, we have for continuous. Now let's begin with an example of a simple Monte Carlo simulation. Using the law of large numbers, we will create a simulation using random values to estimate pi. Due to the large number of random samples needed to fulfill the law of large numbers and get an accurate expected value, it's going to be easiest to use computer simulation, particularly through code. However, if you wanted to do a very long and painstaking way, you could do more traditional randomization methods, such as using a random number table. So the theory behind Monte Carlo simulations is that you're able to pull many random values to approximate some value. When using this technique to estimate pi, imagine a circle of radius 1 circumscribed by a square of length 2. In this image, you see it pretty clearly. You have your circle of radius 1, your square of length 2. It's apparent from the ratio that pi divided by 4% of all dots placed randomly will appear within the circle, hinting towards the value of pi. This makes sense as the area of pi is, or of a circle of unit 1 is just pi, and then the area of a square of length 2 is 4. So 3.1415, whatever, divided by 4% of all dots randomly placed in here, in this box, will land within the circle, giving us an accurate depiction of pi. So here we use a Python script to prove this point using its randomization function. So here's a little Python code that I've strung together. By no means I'm a computer science major, but this will do the trick. So here, and the actual IDE where you can actually run software is what I have written down. So we're going to look at the number of circles we have, or the number of random dots, and see how many of them will land inside the circle. This is what our variable is. Variable inside circle is the number of dots that will land inside the circle. And then we're going to create a for loop, which is essentially going to be our number of random trials, which we set by this num samples variable. In this case, we're just going to do 1,000,000. So this will just run 1,000,000 times. So you're going to give yourself a random x coordinate of any value between 0 and 1. Obviously, that's pseudo-random numbers is not entirely random just because that's how a computer works. It's almost impossible to create true random. And then we're going to do the same thing for x and for y. And then we're going to calculate whether or not these, which are going to be in the first quadrant, fall within a circle, the circle of length of area 1. Essentially, just finding which ones land within our circle as seen before. Then you're going to multiply that by 4 because we're only looking in the first quadrant, which then returns your estimate for pi, which will print. So in this example, we're going to have, so start with 1,000. 1,000 samples. Not quite accurate. 3.22 is not pi, unfortunately. But watch as we increase the number of random samples. And this will be due to the law of large numbers. A lot closer, 3.14. You're missing the 1.5 part. However, you've got a pretty accurate up to three decimal places estimation for pi. So that's a basic example of how you could use a Monte Carlo simulation to estimate a value that you are struggling to find. However, pi is not the greatest example. There's so many other ways to find pi in a more rigorous and more apparent way that Monte Carlo solutions aren't exactly super useful. However, an example of where you would want to use a Carlo solution is in the world of finance. Um, Monte Carlo method is useful when there's no definite solution or it's close to impossible to solve. But now let's imagine the world of options pricing using the geometric Brownian motion formula, an important concept in finance. This is talking about, if you ever watched the movie The Big Short, talk about variable pricing and options pricing so that you can make an accurate decision of how much your asset is worth so that this can be priced fairly on the market so you don't create a massive shortage or a massive oversupply. So S of T is the price of your matured stock value. S sub zero is the price of your initial stock value. And then E to mu being your interest-free risk or your risk-free interest rate minus the volatility squared divided by 2 times the time it takes to mature times your volatility times a random walk. The random walk variable is what we're going to use the random trials to discuss because this is essentially how much volatility is there in the market as a whole, which is almost impossible to tell. However, does line up nicely with the normal distribution. With options trading, there are two options. You can either sell what you have or you can do nothing. This is represented by taking each value as S sub t and then taking its maximum against the value 0, because why would you sell if you're going to lose profit? Or there's no reason to. Um, so it's going to be easiest to describe once we get into the actual code that I've written. So we have, just for sake of argument, we have S sub 0 being 100, your strike price, which is the price at which you're allowed to sell, being 110. Down to mature in years is 1. Risk-free interest rate, which is kind of high for right now, would be 0.5. Volatility stock 0.2. And then again, like we saw in our first discussion, the number of samples, which again we'll start with 1,000,000. So here is the Z values. These are going to be what our random walk values essentially are. Since the volatility of the entire market, there's a lot of samples, it means that they're going to, by assumption, stay within the realms of the normal distribution. So Z is our random distribution. We multiply this together using the GBM formula. And then here's what I was talking about before, where you use your strike value or your current value of your stock minus your strike value K, because if K outweighed S T, you would not want to sell, and you would just keep 0. And then since we're talking about the prices in the future, we need to discount the price back to the present, which is our options pricing. So this is a lot, but let's see how it runs. So when given 1,000,000, let's start with 1,000. See what our average stock price is with 1,000, or our average price of this option cost. So 6.15. It's actually pretty close. Let's run it again with 100. 428. You see a pretty large distribution there. Then 687, kind of scattering all over the place. But as we increase our number of N, we see that we converge around 601, 604, that number. This gives a better estimation as to what our stock value is. It allows us to kind of set a marketplace value, even though that finding the actual solution of this would be almost impossible because you don't know the random walks in the market. This Z value allows us to approximate these random values, which gives you a better guess as to what your asset is worth. So in short, the Monte Carlo method is useful because it allows you to use random samples to approximate very difficult solutions. And this is applicable to all fields of finance, physics, or anything that allows you to use random variables to represent any sort of deviation in your response. Thank you for your time, and I appreciate it.